Okay, so here we go. We're talking about probability today. Very first question. This is called a contingency table. It's such a small one that it could be just considered the data. Let's read it quick. The table below shows how many bottles of each type of fruit juice were sold from a vending machine on a randomly selected day. How many of the next 500 people who buy from this machine can be expected to buy apple juice? Now, sometimes you don't even want to actually try to start the problem right away. You just want to make sure you understand it. All right, so there's these different amounts of the different kinds of juices were sold. And if you add them all up, that seems kind of important to do. It would add up to 20, 40, 60. You get how it adds up to 60? So now, if I were going to figure out the probability of apple, it seems important, right? Even though I don't know what to do with this 500 yet. What do I do to find the probability of apple? 18 out of 60. Now, why do we do 18 out of 60? Because it's what you want over what things were possible. All the things that were bought were 60 things, and 18 of them were apples. So I divide that and I get a decimal. Then what do you think I should do with the decimal? Times it by 500. That's all there is to it. But it reminds us a few things. Number one is take your time on a word problem and read it, make sure you understand it. Then it's almost always going to involve a number on the top divided by a number on the bottom. What you want on the top divided by what's possible. All right, let's look at the next question. We go down to, I'm not going to go through all of them, but I'm going to go through the ones that are alike, or the ones that are different, I mean. Okay, so this one is an actual contingency table. Remember, what it's out of is really important. If I said, out of the juniors, what's the probability I'd pick a morning person? Do you get how I'd narrow it down to out of 28? Because that's what the juniors is out of. But if I said, what's the probability of picking a junior who likes morning classes? Then I didn't say I narrowed it down to just the juniors, right? I said, a junior who likes morning classes. So then I'd say 6 out of what then? 129. Because I didn't say it was just juniors, so it would be out of that. Okay, so what it's out of is kind of the important thing. You'll know what to do with the 6 that goes on top either way. But the question is it out of 28? Because if I said it was only going to be juniors I picked from, then it'd be out of 28. If it's out of everybody, it would be out of 129. All right, so that's important stuff. Next topic here. Scroll down a little bit farther. That's the same, basically. There's one little tweak in that you'll notice is different. On to this one, it's Venn diagrams. Do you remember if I say or? Is that, yes, or is the big answer. Okay? And so or would mean if I have a probability to pick a sophomore or somebody on a sports team, that and that would all work, even though it's or. Or is the big answer. Add them all those up. Okay, what if I said probability of picking a sophomore, the person has to be a sophomore and be on a sports team. You see how it narrows it down? If I say probability to pick a sophomore who is also, or and, the person is a sophomore and is on the sports team, then it would only be that one. So and is only the middle one. Or would be all of them circled, except which one? The 605 one. That would be if it's neither, if it's not a sophomore and not on a sports team. All right, so pay special attention to what it's out of too. Because if I said, if I only pick from the sophomores, what's the probability I get somebody on a sports team? Then it was only out of these two. That's what goes on the bottom then. And what I wanted if somebody is on the sports team, it would be that out of all of that. And you wouldn't even use those if I said I was only picking from the sophomores. All right, so what it's out of is really important. That's the hardest part. All right, moving on. My computer's freezing up. There we go. Okay. Next kind is, this is basically just where you draw a Venn diagram. Okay, so you have to make your own for that one. This one is just your classic marbles in a bag problem, and it's, you know, the total marbles in the bag is 15. This would be a really easy one. Moving on to this one. You got 2 dice are rolled and the numbers that result are added. Find the probability the sum is an even number or a number less than 5. This one's a lot harder than you'd think. Because to find the probability of getting an even number, I got to add up the probabilities of all of the even numbers, right? What's the probability of getting a 2 when I roll 2 dice? 1 out of 36. Remember, there's 36 things that can happen when you roll 2 dice. That's the probability of getting a 2. What's the next one I got to check out? 4. What's the probability of getting a 4? How many ways can you get a 4 out of 36 ways possible? 1 and 3 and 3 and 1, right? Oh, and 2 and 2. So that's 3 ways. Do you get what I'm saying? So you have to add this, plus, and then you'd find out the probability of rolling a 6. That one's pretty likely because it's really close to a 7, which is the most likely. So this one would be how many ways to get a 6? I think it's 5 ways to get a 6 out of 36. Get what I'm doing here? Okay, that's how you'd find out the probability of all the even numbers. And then we got to also throw in or, which means makes a bigger answer, so I include more things, or a number less than 5. Well, I've already done 2 and 4. I don't have to do them again. Do I have to do 5 if it says less than 5? No. What else would I have to do then? 3. So you'd have to add in 3 into your list and see if, what would be the chance of getting a 3? I think there's 2 things that make a 3, a 2 and a 1, or a 1 and a 2. And then it's out of 36. And you'd add all of those up and you'll get your answer that way. So that one's a little more complicated than you'd think. Okay, next kind. This is area model of probability. See the little picture that's got the shaded, hold on, having issues. It's got the shaded in area. And one big little, just a little thing that kids forget is to do a triangle, you don't just do 10 times 25. You do the base times the height, which is 10 times 25 for that shaded region there. Divide by 2, very good. And you always take what you want and divide it by what's possible. I hope you're sensing a theme there. All right, next topic within probability is tree diagrams. Remember how you can draw a tree? This is the kind where first you have to do the whether or not they take a class, a ACT prep class. So it's like these kids take one, take ACT prep, and these kids did not. And there's a 45 chance and a 55 that they did not. Then of the kids that took their ACT prep, they have the numbers for that. They're more likely to get into their first choice college. 78% get into their first place college if they take an ACT prep class. And I encourage you to consider taking one of those, just in the real world. It can really help you focus in, and you probably get a better score than you did the first time. Because you know what happens if you don't take the ACT prep class and then you take the ACT and then you get a score? What are you always going to wonder? What if I had taken one of those prep classes? Would I have been able to do better? Know what I mean? So I think if I had it to do over again with my son who took the class, he got a 29 as ACT. He was pretty good, but he wondered, oh, if I had taken one of those classes, would I have done better? So now he's going back and taking the class, and now he's going to take it again. Okay, so if we had just taken the class in the first place, then we'd know this is the best score we could have got. And he's trying to get into the Air Force Academy, and so you need a really high score to get in there. 29 is kind of average at the Air Force Academy. So he has a chance already, but if he can get like a 31 in his ACT, he'll have a really good chance of getting in the Air Force Academy. So. All right, so back to 78%, and then this must be, what do these have to add up to? 100%, so this would be what? Is it 12? 22, I think you're right. Okay, you get the idea of how to draw the tree diagram. Then, moving on to number 12 and 13. These are those P and C kind of questions. Okay, if they have first and second place in a spelling bee, do you get that the order matters then? Okay, remember the order mattering or not mattering is a permutation or a combination. Okay, permutations, the order matters. So in a race, if you're in track, does it matter if you're first place, second place, or third place? Yes, it does. Order matters, right? Okay, so then it matters, and it's you'd use a P for that. If I picked 3 of you to help me, you know, clean up or whatever, would order matter? No. And therefore, that'd be like a C. All right? Do you remember where to find that in your calculator? Let me show you. Grab your graphic calculator. If you don't have one, borrow one of mine. Right here. Okay. It's under math. So first thing you do, let's do one. For this one, we're going to do the actual problem, number 12. There's 10 kids, so we're going to do 10. And I told you order matters, so it's P. And then there's how many places? First and second, so there's 2 places. So we want to do 10P2. So type in a 10. Then go to math. Then arrow over to probability. And it goes like this, NPR, that's the button you use. And that's, again, under math, PRB. So you go 10, P2, enter, and it looks like this on your calculator. 10, and then that, and then 2, and then what do you get, by the way? 90, and that is one of my choices right there. Okay? All right, so there's a reminder what P's, order matters. Maybe I should start saying order patters. Okay, anyway. On to 13. This one is where the order doesn't matter. So what am I going to use for that? C. All right. And if I have 3 tosses of a coin that have exactly 2 heads or 2 tails, you have to start thinking again, what is it what I want? I want exactly 2 heads. Okay, that's out of 3. So which of the ways that I could toss this coin would I want? Well, maybe I should make a list of all the ways I could toss if I'm going to toss it 3 times. I could get heads, 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 right? I could get heads, heads, tails. I could get heads, tails, heads. Tails, heads, tails. Is there any other combos? Oh, yeah. Tail, tail, tail. There's more. Tail, tail, head.
Tails, heads, heads.
Tails, heads, heads. I already got head, head, head. Head, tail, tail. All right. Is that all of them now? 1, 2, 3, 4, 5, 6, 7, 8. That doesn't seem like a logical thing. There should be more than that. Is there anything? Can you think of one that's missing? Heads, 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 tails, heads, tails, heads. Tails, 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 heads. All right, let's assume that that was right. I feel like there's something missing here, but okay, let's assume those are all of the possibles. What are the ones that I want? I win if I get exactly 2 heads, or, which means add it together with, exactly 2 tails. Which one have exactly 2 heads? That one does. That one does. That one has exactly 2 heads. And then I find the ones that have exactly 2 tails, and I add them all up, and I put it out of, I guess, 8. I still feel like there's more than 8, but since I can't figure it out right this second, I'm going to move on. You think it's C? Well, then maybe it is out of 8. Could be. Okay. For some reason that just doesn't feel right, but I've been wrong before on that, which is why I thought it was okay to just move on. All right, so the other problem will be a lot like that. Now let's go down to 16. You're only doing up to 18 today, at least in my classes. I don't know if you're watching the video and you're in one of the other teachers' classes, you might want to look. But in my class, we're only going up through 18. Number 16, a coin is tossed and a number cube is rolled. 2 different things. What should I do with them? Times. Almost always you're multiplying when you're doing probability. You're multiplying fractions a lot. All right. And this one's the one where you got a whole bunch of different kinds of jelly beans, and replacing or not seems to matter. Why does it matter? Because if I put the jelly bean back in there, the probabilities reset to what they used to be. But if I take a jelly bean out and I keep it out, now my probabilities are all different, right? That's called independent versus dependent probability. And if I take that jelly bean out and I take it and I keep it out, then that was a dependent problem, because what happens now depends on what jelly bean I had taken out. All right, I think that's enough review. Oh wait, one last thing. The last question is number 18, which is one of those expected value problems. Remember that those kind are definitely on the test, and if you're going to do a expected value, always make a little tree, and it works or it breaks. Find the probability times the amount that you'll get if it happens. Let's say that there's a 5% chance of it. No, it'd be 95% chance of it working and a 5% chance of it breaking. And you times by the amount you get. If it works, you get nothing usually. They don't give you anything. In fact, you lose money because you paid money for a warranty. And if it breaks, you get the money that they pay you for the warranty, and you put that in here. So these are the amounts you get. You multiply them, P times the A's, and then you add them all up. Okay, there's a reminder of everything you need to know. Your assignment for nights 1 through 18. And we're going to go farther in the packet, of course, on Monday. If you wish to work ahead, you may. We are going to eventually do every single problem in the packet, but we do have all next week also. Okay, that's all I got for you for today.